Unreal Header Tool, or UHT. What is UHT? If you've been programming in Unreal for a while, you've probably seen UHT or Unreal Header Tool mentioned. Unreal Header Tool is a tool that first reads your header files, or your .h files, and then second, UHT generates files based off what it reads in those header files. And it adds features to effectively the C++ language. So here we have this UPROPERTY system that prevents these from being garbage collected. And we have regular C++ variables that do not have UPROPERTY, that are not part of the garbage collection system, but these are features that have been added. We have UFunctions, which allow functions to be called from blueprint scripts. We have things like make them pure, which changes how they look in scripts. We have blueprint implementable events, which is just an event that happens on blueprint side. We have blueprint native events, which have native callbacks. All of this is features added. We have things like RPCs that execute on the client, or it executes on the server, or it executes everywhere. And these functions get mapped to these underscore implementation functions. And it all seems rather automatic and magical if you're just writing the code. But if you drop a breakpoint here, you can see that there's a lot going on here. So something has worked its magic here to make this work. And it also adds features like an onRep callback for when this variable replicates down from a server. In the CPP file, we do a little bit of setup, but we're not ever actually doing the setup for this onRep. Like, that's not mentioned down here at all in this lifetime property setup. This is just marking the property dirty so it knows to replicate, and this is just setting up some properties about this replicating using the push model. Also, there's this cheat display all where you type the name of the class and then a property name, and you get these debug views of what the property currently is. And all that we've done here is just add a property that is set to 2 by default. UHT also adds new compile errors that guide you. So in this case of setting an RPC, it needs to know is it a reliable or unreliable RPC, and we forgot to do that here. And so it generates a compile error here, letting us know what we need to do to fix this and make it work correctly. So why look deeper into UHT when these files are generated? You're not really supposed to have to worry about them. Sometimes you can have natural compile errors show up in the generated code. So here's 2 cases where I have ZConstruct showing up as compilers in this .gen file. And this is actually user error on my end, but I'm seeing the error first in this .gen.cpp file rather than my code. And so sometimes these generated functions also show up in call stacks. And just having an understanding of a high level what's happening, what's being generated, can really help you diagnose these. In this case, I just need to link a module. I mean, you can see my videos on Niagara and Metasound for that, but it's a really trivial fix. Knowing a little bit behind what's being generated helps you diagnose this and solve it. So the first time you write a UCLASS, you've probably noticed some things. You have to prefix it with UCLASS and denote some properties here. You have this generated body thing. Your properties have this UPROPERTY macro. Your functions have this UFunction macro. And if you're curious to see what these macros evaluate to, and you start following the definition, you'll be surprised in that you'll find they don't really evaluate to anything. So if we follow generated body, we see it's defined here as this macro combine current file ID, line number, and this generated body thing. But if you start searching for these, you just don't find them. And then the same thing for UPROPERTY and UFunction. If you go to the definition of UPROPERTY or UFunction, you'll find that they're not really defined. But you will find this text above it saying parsed by Unreal Header Tool. There's also another curious thing. If you forget to include this .generate.h file in your header file, you'll get a compile error. And so in this case, I have this header file here. There's the same name with a .generated.h. And if I forget to include this, you get the given include must appear at the top of the header, following all other includes, include this. So it tells you what to do. And so this is rather explicit that there's some generated files happening as part of Unreal Header Tool. So what files are at play? We have the standard header file that you write, and we have a CPP file that you write. But the UHT process will generate this .generated.h, which is a header file that is included up here. And then it'll also generate a file.gen.cpp, which is its own translation unit, which provides bodies to some of the functions injected from this file. So if we were to take a look into these files, you can see how this starts to work. We have the generated body here, which defines these macros, which adds functions that just get populated right there. And I'll go a little bit more into detail about that a little bit later. But we also have the property here, and so there's things here related to this property. And then we have the function, which also has things related to this function in the .gen file and the .generated. And so these things show up in different places. The generated body is in this file.generate.h. The property stuff mostly shows up in the file.gen.cpp. The UFunction stuff shows up in both the generated.h and the file.gen.cpp. So where can you find these files? Well, my project is UECPP tutorials. Nested in there is an intermediate folder The intermediate folder is like a temporary folder. You don't generally check that in because this stuff is just generated code that gets changed and you don't really want to bother tracking all of that and get her perforce. But if we go into this folder and follow this path, you'll see that there's all these .gen.cpp files and .generate.h files. And this is for the project. If we look for plugins, for example, I have a plugin here, test dependency plugin, and there's an intermediate folder in that plugins folder structure, and you can drill down into that to get to UHT and find some generated files there. So let's explore regular C++ compilation and then compilation with UHT involved. So this is a rough approximation of what happens. There might be a few mistakes here, but you can roughly assume this is how it works. So in regular C++, we have a set of files, a header file and a CPP file. So I have a file called A, a file called B, a file called C, and there's a header and CPP file for each of those. First, we run the preprocessor, which effectively copy-pastes the header file into the CPP files. And we're really only left with the CPP files. These are the translation units and are what are actually going to get compiled. The header files are effectively copy and pasted into the top of these. You can see here where I have some fake includes. This one includes all three, and we see that it got all three headers copy-pasted into this one translation unit. After that, we run a compiler, which changed it from this form into these .asm forms, which is assembly language. Then we have the assembler, which converts the assembly instructions into binary. Then we have the linker run, which links all these translation units together and allows them to call functions amongst each other. That's a really rough summary of how C++ compiles and works. But if we consider it with UHT and how that works, we start out with the same set of files. We have this header file, CPP file. We run UHT, which then generates .generative.h files and .gen.cpp files. So from these 6 files, we now have 12 files. And then we run the preprocessor again, same step. And that preprocessor copy and paste all the h files into their .cpp files that are needed. And we get this sort of intermediate form. And then we run the compiler, which builds our assembly files again. And then we run the assembler to get binary files. And then we run the linker to link all the binary files again. And I tried to show the picture here. In a normal case, we would have had 3 files kind of linked together here. But now we still have those 3 files, but these kind of adjacent .gen.cpp files that are also compiled, which came from UHT. And so that at a high level is how it works, at least from my understanding. There's some additional files, but we'll get to those later. Now there's a few things to understand before we dig into these generated files, but just to give you a quick preview, this is what the .generate.h file looks like. A lot of macros in here. And I've went through and labeled what these things are roughly doing, at least as far as I can figure that out. But we'll explore that later. This is roughly what a .gen.cpp file looks like. So this is something actually sent to the compiler to compile. And I've labeled those also. And again, we'll get into that in a moment. But before we analyze the generated files, things will make a lot more sense if we understand some concepts first. So let's review some things. Reflection is a language feature provided by some languages. So here I have an example of C# and Java. And what reflection lets you do is kind of like looking in a mirror of a type. It lets you change things about a type without really knowing things about the type at compile time. In some ways, it lets you change things about classes by introspecting it. So if we look at the C# example, it'll make more sense. I have a class here and it just has a float property and it has a function. And we don't actually call these directly. Instead, I have this main method testing it, and it uses reflection to manipulate the object. So instead of using the object, we say get the type from the object, and that's the reflected type. The reflected type, we're able to get the property with this string name, myFloat, which is able to find this thing. And then we're able to read the value if we pass in the object to read the value from, and we get the value, and we cast that to a float, and then we can read the float, and we see down here that the value is 5 is printed, which is what we had set. We can also set the value on the object to a value of 10. We see down here, it printed. I was able to read it. And I did a cast to the object to read it directly in this case. So this was a direct read, just to make sure that changing it this way actually propagates to the object. And then lastly, we can do the same thing for functions. We can request a function, myFunction, which is right here. And that internally prints out and then returns a number plus 2. And we invoke that function on the object, and we give it some parameters of 5. And then I'm able to see a result, which is an int, those matched here. I casted it to an int, and then print the result, and we can see it actually printed 7. So it took that 5, added 2 to it, and printed 7. And this is all like an indirect way of calling functions and methods. And then here's a Java example. It does the same thing. So this is C# version and Java's version. But using things like I just showed you isn't really the power of reflection. Instead, reflection allows you to do really cool things like create generic property windows in like a gameplay debugger or some sort of tool. And we could, in theory, use this to write to properties. So you could build like a property window that just says, oh, there's a float, let me type a thing in, and it'll pass that value into the object without ever having to write specific code that says, oh, let me change the thing called myFloat. That's really where Reflection's power comes in. But Reflection is missing from C++, and it's been missing for a long time. There are some proposals to add Reflection. Looks like currently C++ 26. But there isn't Reflection by default in C++ like there is C# or Java. However, a lot of people have built Reflection systems. So if you search for C++ Reflection under the language C++, you will see lots of repos that appear to have built their own version of Reflection. The point is that lots of people build Reflection systems to add it to the language. And Unreal is no exception. Unreal has built its own Reflection system. So why am I talking about Reflection? A lot of the generated code is around building a Reflection system in a large part. And so understanding Reflection kind of informs you what's being built and gives you some understanding of what you're seeing. And so the first thing is for UClasses. So here's UClass. There are two related things. So if you look into the code, you'll find that there's this function called getClass. There's also a StaticClass, and they return this UClass pointer. So this is its own type, and this UClass effectively seems to represent the reflected properties for a given class. And so the getClass gives you the most derived thing. So if a blueprint is inheriting this type, this will give you the blueprint, as you can see there. The StaticClass gives you specifically the thing associated with that type. So ignoring the whatever the current object is, just get the static reflected class here. But generally, you probably want the getClass method to give you the derived most class. And so you can see here, I have this class and I have various properties. I have functions on it. And here we can ask the class, the UClass, to find a property by its name. And I just have a string for this name, myFloat property, which is right here. And same thing for my blueprint callable, find function by name. This is the name. You can see my blueprint callable function is right there. And it's able to return these reflected types like f property or u function. And just so you know, you don't have to like type a string every time. There is a macro to help you do this type of thing called get member name checked, which is kind of a compile time check to make sure it actually exists, that property on this type. And same thing for function. Get function name checked and get member name checked. And so we have this ability to kind of request a UClass to get reflected data about a given class. So you can see how this is starting to resemble the C# and Java that we looked at. And this is actually extremely useful for other things that actually are gameplay. So for example, if you wanted to spawn an actor in the world spawn actor, say we want to duplicate, we can get the derived most class like this, get class, and we can spawn another one somewhere in the world using the world spawn actor. And so this is able to take this UClass, the reflected class, and somehow translate and instantiate this C++ class. And so this thing is a blueprint class. So we're able to do this without ever writing code that exposes this blueprint type to C++. So this is a really powerful feature. It's perhaps a little subtle in understanding it. And then there's other features that are useful from this reflected thing. So you can get this superclass, which can be used in various ways. You can get the interfaces for that given class to iterate and see if it has an interface. There's better ways to check that, but perhaps there's a different use you have here. And the more you look at this, you start to see that it's pretty widespread, the use of reflection in the engine. For example, here I have a data asset, and this data asset spawns an actor class. And you've probably seen T subclass of, and you specify the type, and then in the editor, you pick the blueprint subclass you want. And then in the world, we can pass that T subclass of to spawn actor, and it's able to do it just like we did with the other one with UClass. And the reason this seems to work, if you look deeper into it, under the hood, it's the same thing as just providing a UClass. T subclass of has a property called class, which is of type UClass. And so this is some examples of reflection being used in regular gameplay as far as the engine is concerned. Since we're on the topic of UClass, I feel like it's worth mentioning the class default object, or CDO. CDO is effectively like a singleton that has all the default values on it. So there's a couple ways to get defaults. The thing you should look at is getting the UClass. So here we have get class, the derived UClass, and then on the UClass, you ask it for the default object of that type, and it gives you back a casted version of that default object. And that default object can be used to restore state. So in this case, I have a float property, default is 5. On this level instance, I've set it to 123. And here I have a function called readCDO that effectively wants to restore it at runtime. So what it does is it requests the CDO, and then it reads the CDO's version of this, which is going to be 5, and it puts that 5 into the instances variable here, and then I log it, and we can see down here it changed from 123 to 5. So that's what a CDO is. It's effectively like a singleton object that has the default values. And there is another get default, which is this here, and this is more typed to this specific class. It won't give you the blueprint class default object. You can see the names here. This is the blueprint reflection tester, and this one is the default UHT my reflection tests. And if you look at these functions, you can see why there's two get defaults. One of them provides a class, the one that gives you the static class effectively, or this right here, the one that gives you the default that is this type and not the derived type. That one uses the static class, and that's why not the current class. This other one that takes a UClass just calls the class get default object. And so that's why there's a difference. Be aware of that when trying to get a CDO, that make sure you call the right function for what you need. And so in the C# and Java code, we saw us writing values back to properties and calling functions. So here's some examples from code that do that. Here we have a function invoked by reflection and a property set in blueprint. So we saw that UClass has an associated UClass pointer. But what about these types? So we have UStruct, UENUM, and UINTERFACE. Well, if we look at a UStruct, here I have one defined. We've got a UStruct, generate body, and then we have some properties. And we can do something like get UClass, but it's the static struct for this struct. And it returns this ScriptStruct pointer, which is effectively a reflected type. We can use this reflected type to find properties, like find property by name, and do reflection stuff there. The same is true for enum. So here's an enum that has two values. There's this static enum function we can call to get a UENUM pointer, which seems to be a reflected enum. And UInterface, we have this UInterface type, and then we have the type you actually inherit from. You can see my video on interfaces about that. That just seems to use UClass. So you can get the static class of that UClass and do some reflection here, similar to what we've seen. And so the reflection system and the engine seems to rely on these like reflected types. So there's like UClass, UScriptStruct, and UENUM, and there's a lot more. So all of those inherit from public UField, and you can see all the different types of reflection types in the engine. And just to make that clear, a lot of these are inheriting from like UField. So we have UClass and UScriptStruct, which are both UStructs, and the UStruct is a UField. And UENUM is its own thing. It's just an inherited from UField. All right, now that we've seen what reflection is, how it's used, how it can be used, what it can do, we can now start going into the generated code. And so just want to give a disclaimer that this is generated code. You're not really supposed to be modifying this stuff. You let it generate. I would not worry about memorizing this, but just seeing what it does at a high level seems to be useful. But this may change from version to version. So each engine version might update this because this is not really code you're meant to be directly calling, but it's just code to enable the features that you're used to when writing C++ and Unreal. But this is just what I found from digging into the generated files in UE 5.4. It may be different in yours. So there's a pattern that emerges. First, we'll look at UClass. There's this ZConstruct pattern. What it seems to be is effectively constructing a reflected class. So it lazily evaluates, do we have this outer singleton thing in our registration info? If we don't, that's not symbol, then it constructs a UClass. And this is what builds the UClass that we can use to read properties and do reflection on. This function here. Here's the call stack of when it gets done in the engine. This is a very early startup thing with loading modules and stuff. But you can see here, here's the construct UClass. Go down to here, you can see a new UClass is created, and there's a no class register func. And if you trace that all the way down, so no class register func, which is in declare class, I believe. And then there's a static class function, get private static class. Keep going. Eventually you find that we allocate a U object and we use a placement new. And then as this progresses, we use some class params to effectively build the U class, the return class. And the same thing is true for UStructs and UScriptStructs. So we have the ZConstruct pattern. If it doesn't have one already, it calls this construct UScriptStruct, and here's the call stack for when it does that, and that's going to return us this UScriptStruct. We can see it does a new operator, and it builds a new struct, and then eventually we set all the properties and whatnot, and so that seems to be how that reflection data is built. Similar thing with UENUM, there's a ZConstruct. If it's not populated, then it calls construct enum, and this is the call stack when that happens during engine startup. And this is what it looks like. Eventually it calls this construct enum and it does a new operator. We get this new UENUM and it does some reflection stuff, iterating over properties and assigning their names or something like that. So you can see here it does some work using the reflected data to effectively build this UENUM. UInterface has a similar pattern, ZConstruct, but this one's really doing the same old construct UClass. Here's the call stack, but it's effectively the same as UClass. Now, to understand what we see in the files, there's a few C++ nuances to go over. Like other languages, there's the concept of member statics. You have a static function and you can have a static variable. How they work, we can call a static function. There's no object instance here. We can print out a static variable. There's, again, no object instance here. The static variable is shared. For the functions, you define the body in a CPP file. Set up a static function, declaration, and then over here is where it's defined. In C++, even though we have the static variable here, we still also have to set up a definition here. So we've declared it here, and we've defined it here, just to show you the static. Additionally, in C++, you don't even have to define the type in the header. The struct or class can be defined in the CPP file up here. So we're declaring the two static variables, but we still have to define them. And so you'll see this pattern a lot in the generated files. It declares a struct, then it defines the struct variables below it. The other nuance is that you can define functions in different CPP files. So this is used also for the .gen.cpp files to provide bodies to functions that were in the .generated.h files. So the normal function is defined right here, normal function. I have an additional CPP file, and here we define the other file function. And this is just a reminder that macros are effectively copy-paste text. Macros are useful for basically copy and pasting functions around. So here I have an example of adding functions to a type based off a macro, which is used in these generated files. So again, the files involved here, we have the header file that we write and the CPP file that we write. And then there's the generated header file and then the generated CPP file. If we take a look at the file.generate.h, the generated header file, we can see there are effectively some macros that get defined, and these macros ultimately get pushed into a macro below that is helping with the generated body. So starting from the top, there's some includes here that provide some macros like these. So it includes some things. There's an include guard to catch, apparently, if you forget some things, like a pragma once. So it catches it here, which probably stops some compile errors. There's this helper macro that defines a class and serializer and some other things. So it friends the ZConstruct. And this declare class does a couple things, like it defines the super, it defines the ThisClass, the static class function, things like that. And then below that, there is this enhanced constructors thing that declares some constructors. And then there's some macros for more advanced constructors, like one that takes a vtable helper and the default constructor. And there's also a virtual destructor provided. If you're familiar with C++, you'll know that we're getting to do this for a polymorphic type. And so creating some headaches. And so the header tool just does this for you. So it's just not a thing you have to worry about when programming with Unreal types. And then below this, there's this generated body helper macro. And that's pulling in these two. There's a function for getting the static class that's a template override. And then this bottom bit is actually really important. It's undefining a current file ID and then defining the file ID to be this long string. If we look at this a little closer, if we go to a type, you'll notice that we have to include the .generated.h before the type. And so that is what defines this thing here. And if we look at the generated body again, we'll see that it points to in the engine this macro combined current file ID, line number, and underscore generated body. Well, this current file ID is the file ID generated right here at the end of the file. And this undefined is probably why you have to put this at the end, because the ones above this change it potentially. So the last thing included will be the last file ID. And this file ID matches up with that. The underscore is here. Line number is 12. Which you'll see the generated body is at 12. Then we have underscore generated body, which goes here. So that defines this macro for generated body. So that's how generated body uses this macro, which in turn uses more macros up here to add functions to your class. If we look a little bit into that declare class, note I did edit this to make it a little more compact. There's a lot of stuff here, and this is in the object macros header, but there's things like the super. So if you ever saw super : and then have function calling the super, that's where the super gets defined from. That's not part of C++, that's part of the Unreal toolset. And same thing for this class. If you're doing like delegate bindings and that kind of stuff, you often can see this class instead of typing out the class each time. So there's a lot of things here. There's like new operators and delete operators, but some of these are for internal use only. But there's like StaticClass here, static package, StaticClass cast flags, some operators. So a lot of this stuff comes from this declare class, which is used in the .generated header. This declare serializer also adds some serializer stuff for archives slots. So that covers the .generated.h file. Next is the file.gen.cpp. So this one is the one that contains a lot of stuff. This is a full-fledged CPP file that is compiled. It's harder to read, so I broke it into two panels here. So you can see this and this, and it does look rather cryptic, but there is a underlying pattern here. So at a high level, there's really two major operations that seem to happen as far as I can see. There's the types setup, which defines all this setup stuff for reflected properties. And then there's the type registration, which takes this and shuttles it off to be registered later. And so I've annotated all this, and we'll go through this now. And so at the top, we have these header files that get included. Again, this is including the actor file that we made, some other includes. Then there's this section called Begin Cross-Module References. And we start to see declared ZConstruct functions. And so if I annotated this with a star, we can see the star pop up later. These are just the function declarations. Their bodies get populated later, except for things like this, which is defined in, I guess, the engine's generated file for actor. First thing is this static register natives, which if we look at another file in this box here, we can see as we populate U functions, it builds this out. And so then there's this implement class no auto register, which gives us some stuff like get private StaticClass. StaticClass defines Z register and info, things like that. And then we finally do get a body of this ZConstruct, the star associates it up here. So this ZConstruct no register, which is just called StaticClass. Below that, there's this ZConstruct UCLASS actor statics. And so this is a struct that uses member statics to hold data. So if you recall the member variable statics for classes and structs, that's effectively how this is working. We have things like this static array that's declared here, and then it gets populated below, like right there. So what it has is some metadata if it's compiled using this compile flag. And that's things like where the actor file path is, the module relative path, things like that. Then we have this dependent singletons array, which is an array of function pointers. If we look at how it's populated down here, it's got the ZConstruct of the parent class, the ZConstruct of the package, which is the project UECPP tutorials. Then below the dependent singletons, we have this StaticClass type info, which looks like it is some type traits for the current class. And this is available at compile time because it's const expr, so we don't have to provide a body for that one. This is the actual definition rather than declaration. But lastly, in this statics struct is the class params. This one is very important. The class params is effectively where we store all this reflected data, and we send it off to basically build the U class in the ZConstruct. So we'll see that in a moment. But if I scroll down here, the class params, when we actually populate it with stuff, there's all this data here, the types. You can see the parameters to this. It's effectively like a register function, properties array, function link array, dependent singleton array. So a lot of things get populated here. And as we add like U functions or U properties, this gets changed. You can see a zoomed out image here that it's adding things for U functions there and adding things there for U properties. We'll get into that in a moment. But then finally, we have this ZConstruct with our actor. And it's doing that pattern again, where it lazy builds the outer singleton and it calls this construct UClass. Notice we're passing in the class parameters here. And if you were to step through this, you would see that the class parameters that populated up here, so it's used to ultimately build that UClass. So this is how it's building the reflection data. And there's a static class function that we use to get the static class. This is like a templatized version. Then there's some vtable constructors that are defined here rather than declared. See the macro here that is just doing a simple vtable helper constructor. There's our virtual destructors body that was provided in the .generate.h file. And then lastly, we have the begin registration, which has kind of got two phases. The thing above it is what shuttles the like ZConstruct functions, static class functions, the name, and some other things. And then once that is built into this f class register info, below there's another struct that takes as part of its constructor the class info, which sets it up to be registered. And so you can trace through that a little bit. That's class register compiled in info, has an outer register, inner register. And when debugging that, I found that to be the ZConstruct function and the inner one to be the static class function. And this gets forwarded to a variadic argument thing, which ultimately registers class info, struct info, and enum info. And all this is engine code rather than generated code, by the way. The generated code is what uses this engine code. And so there is a deferred register. And so registration of the reflection data is deferred. It seems to be called at a later point in engine startup. So while it sets up all this static data, it's not used until later, it seems. And so if we trace through this, we go to what I was showing before, this compiled in info, variadic arguments, where we have the classes, structs, and enums defined. It does register here. It's register compiled in info, and ultimately this is going to call this thing, which gets a deferred class registry, and it adds a registration to it. And so this is what's going to ultimately call the ZConstruct. And so there's two of them. There's the inner register and the outer register. And these are what the call stacks look like if you were to drop breakpoints in the ZConstruct functions. This is when they get called during engine init. And the outer register is the one that contains that ZConstruct UCLASS, and so that's what I focused on here. You can see these outer register functions. And ultimately, that outer register is going to call this function here, which for the first time, there won't be one of these. So it's going to construct the UCLASS and build us the properties for that UCLASS. And here's the full call stack for when that happened for my UHT actor class. Again, that goes into the struct UCLASS, which down here makes a new UCLASS. And as part of this process, it fills out all that information from the class parameters. And so it's worth noting that at the bottom, when we register things, this is from another file, if you put multiple types in a single file, it sort of registers them all at once. So it populates its enum info, it populates its scriptStruct info for UStructs, and it populates its class info for UCLASSes, and then it registers them at the bottom here. So these registrations happen kind of like as a group for everything in the file at the end of the file. So now that we've seen how those files work, we can look at what happens when we add things that use like UProperties and UFunctions. So the way I've done this is I've basically took the file and then made changes to it and using a diff to see the changes. So you can see here we've added a myFloat property and it's a U property, edit anywhere, blueprint rewrite. And this was in the header file. In the CPP file, we didn't really need to change anything, so there's no delta here. There's nothing that changed about the CPP file. And now for the generated files, there actually was no change in the .generated.h file either. So nothing changed in the generated header. But in the .gen.cpp file, or the generated CPP file, there were changes. Now I did modify this a little bit to kind of clean it up, effectively just adding new lines and allowing text wrapping. But you can see the changes here. Since we added this new myFloat property, we now have metadata for it in the category and class. So that like the category gets this class name, module relative path gets that. We have this new static member variable here, new prop myFloat property, and we also get a prop pointers array here. And if we look at where this is defined, it actually defines a lot of data for this property. There's the name, this property flags thing, some more flags here, some offsets, things like that, an address and the ZStatics. And if we scroll down to our class params, you can see that the prop pointers is populated now, whereas before it was not. And we get an array size, so this array holds all our properties. And the registration is mostly unchanged, just this number changed. So the next question I had was, well, what happens between a raw U property that has no markup and one that has markup? So if we make this change, the generated.h file doesn't change, but the .gen.cpp file does. So we get this category that shows up and the type there. We also get this number to change here. So it went from 0 to 5, and the registration is mostly the same. What was interesting is that 0 to 5 is associated with this eProperties flag. If we find that in the engine, you can see that 5 is 4 and 1. So the 4 is blueprint visible and the 1 is blueprint edit. And so this is likely related to edit anywhere, and blueprint visible is likely related to being blueprint read write. So we can add a blueprint callable U function to this header to explore what changes when we add U functions. To the CPP file, this time we need to give the function a body. And this time the generated.h file, the generated header, does have changes. It has this declare function macro here, which we'll explore in a moment. And it has a new macro here that is injected as part of the generated body. And that macro is just basically calling that declare function. The .gen.cpp file has quite a few changes to it. The first is that there's a ZConstruct type for the function itself, the myBlueprintCallable, in addition to the actor. So it has its own metadata here. It has its own function params. So if we look at the function params being populated for that declaration, it's got the name, it has this eFunction flags, which is similar to the uProperty flags, and various other things here. It has the pattern of the ZConstruct doing a kind of lazy creation. It has a local static for the return function, and if there's not one there, then it constructs a U function, which appears to be a reflected type, similar to UCLASS. And it does that in a similar pattern to construct UCLASS. And then below that, there's this define function, which has some macros right here. And ultimately, it is calling our native function here. So this is, I believe, a hook for the VM machine. We'll explore that a little bit in a moment. And then at the bottom, we have the static register natives function for the actor. So this got populated with a function now. And it takes the function name and it maps it to this exec prefixed version of the function, which is defined right there. And we'll look at that macro in a minute. If I scroll down, we have function info now. So this const expr function array has the name and the ZConstruct function address. If you look at the class params, it populates the func info from right there and sets the array count. So this is going to be provided to that UClass when it gets constructed. If we scroll down, the registration is mostly the same, just some number differences. So I was curious what happens when we go from a raw U function, like used on onRep callbacks or dynamic delegate bindings, to one that's blueprint callable, so the blueprint script can call it. The .generate.h file did not change, but the generated CPP file did. And so the main thing that changed was this number here. There's a 4 there and a 0 previously. And this is part of the E function flags. The registered info is mostly the same, just different numbers there. And so if we look at what that 4 is, we can see here that 4 is related to this thing here, blueprint callable. And so when we add this, it just puts it in this bit vector there. And so next I want to take a second to look at this define function. So it defines this exec function, and then it has these string of macros. If we look at the define function here, you can read the comment on it, and this is in object macros.h. It is used to define a function in auto-generated boilerplate code. And these are used in this other script macros.h file, which appears to be related to the Kismet VM execution engine. So this define function literally just makes a void function with a object context, some sort of frame thing, and then this result decimal. So that's what this is doing here, it's defining the function. And then get property appears to create a property for z_param here. So get property name, and it just makes a variable type. And the pfinish does some sort of opcode thing. So pnative begin starts some sort of scope thing, maybe related to performance capturing. And pn just closes the bracket for that scope. I'm not 100% sure what that is. And then the pthis effectively calls the function that we write. So this seems to be a way to get Blueprint to effectively call our native function. You can see this in the call stacks, and so that's my interpretation of that. It might not be 100% correct, but this exec function is put down here in the funcs array inside of this static register native funcs. And that's it for the generated code covered. And so I just want to call it, remember, this is generated code. I don't think it's important to memorize all that stuff. It can change from engine version to engine version. Since you're not really supposed to be calling that stuff directly, it's all generated boilerplate, that may change. And for normal development, you don't really need to explore these files too deeply. You can do a whole lot without really knowing anything internally to those generated files. You just learn the things to do in the header files and CPP files. So while you're mostly isolated away from these generated files, it's good to be aware of. And I wanted to call it that now that you know what reflection is, like, don't overdo it. I have an enum here, and I'm reflecting that enum. If I find references on second value, it doesn't find this. This is just a string comparison. And so if you go crazy with reflection, it can make the code kind of hard to follow. So I would do it for tools and things like that. Just take care to use it when it's actually useful. Additionally, there's a few extra special files to talk about. There's the timestamp file, the ProjectClass's.h file, and then the ProjectNameInit.gen.cpp file. The timestamp file just seems to be a list of header files that were parsed. At least that's all I can see that it's used for. Not sure how it's actually useful. The ProjectClass's.h file is empty in my project, so I'm not really sure what or how this is used. And then this project.init.gen.cpp. This seems to have the ZConstruct for the package for the project. So it does that same ZConstruct pattern that we've seen, and it builds a U package reflected type. There's also some things in here in regards to delegates. But other than that, this file is rather small compared to the other types of files. And let's see the comments for corrections, concerns, comments. And I hope that helps kind of demystify some of the more magical part to the engine. So there's still a lot I don't know about this stuff. So again, I don't think you need to memorize the specifics of that, but just having a high-level overview of what you think is going on, understanding what our header tool is doing for you. It's using C++, and it's generating the tedious parts for us so that we don't have to write as much code to get those features. So I hope it helps, and until next time.